My name is Micah Melling. I'm a data scientist in Kansas City, and I wanted to share a bit about a project that I've been working on. This specifically deals with a statistical analysis of Kansas City weather patterns. This is something that I am particularly interested in because I've lived in the Kansas City region for most of my life. And we've had some pretty harsh winters the last couple of years, which had me wondering, are these unexpected? Are temperatures becoming more variable? And of course, as a data scientist, I thought, well, I could potentially answer this question with statistics. And so this is just an update video on what I've done. I think some of the statistical methodologies have been applied perhaps novelly in certain cases, and this is something that I want to build on, but I also invite others to build on as well. And I want to keep this video fairly informal. I'm going to walk through some of the approach, I'm going to walk through some of the data, I'm going to walk through some of the results. But again, for anybody who's interested, feel free to reach out to me if you're interested in collaborating on this or extending it. There is also a GitHub repository here that should have everything you need to get going. The code here is fairly decent. It's not the best code that I've ever written. My focus has been more on the statistical application side of things with this particular project, but the code should definitely still be serviceable. If you're looking for better code examples, please refer to some of my other repositories. And I will apologize in advance. My cat Quill is sitting on my lap for this, so hopefully he behaves himself. But again, I'm fine to keep this one a little bit informal as well because I'm just looking to share some of what I've done. All right, let's kind of start walking through some of the data specifically and some of the data cleaning that I did. So the data was pulled from the Midwestern Regional Climate Center's online data portal, and it was pulled earlier this year. So as I'm recording this, as you might have seen on the last document, we are in April of 2025, so I pulled this data in February of this year. So let's take a look at what the raw data looks like. It's fairly clean for the most part, but as you'll see, there's a header here that of course we need to remove. This M is for missing, so there's data that we are just going to have to throw out. But it's tabular data on a daily basis. We have precipitation, how much was snow, how much snow occurred, what was the snow depth. So if you had multiple days of snow in a row, that would accumulate. What was the max temperature? What was the min temperature that day? What was the mean temperature that day? So these are really the variables that we will analyze. And in particular, this initial stab at the analysis really focuses on the max and min daily temperatures. So this is all well and good, but of course we need to do some data cleaning, which is in data clean and clean.py. So I kind of talk through some of the just very basic data cleaning steps that I take here, and that will produce data clean kc weather clean.csv. That's also pushed up to the GitHub account, I believe, so you can just pick up the clean data if you would like. And that's useful, but we need to engineer more features and prepare some summary statistics to analyze as well. So as I noted in my introduction, this is not necessarily the best code that I've ever written. So I have a few to-dos throughout here. So for example, this main function should be a little bit more configurable. So instead of hard coding a cutoff for an extreme low, that should be passing up here. But what this function does is it generates variables, some temporal variables for like what month we're in, what year we're in, the quarter we're in, the season. It'll do simple things like what's the intraday range of the temperature. It'll also create segments of years. So instead of just looking at, 1889 versus 1890, it'll chunk years into, say 10-year segments that can potentially add some statistical validity to what we're looking at here. And so there's a decent amount going on in this function, but this will produce both kind of a raw file with some engineered features and then a file of summary stats that we can also work with. So this is what the full file looks like. So again, this is daily data. And apologies, you may be hearing my cats. My other one, Leo, just came down to disturb Quill. Again, we're keeping this informal here. So daily data, and then with, what's the max temperature, what was the min temperature, so we just changed the column names a little bit, but then we've extracted out what year we're in, what quarter we're in, what season we're in, what month we're in, if we've assigned this to a year segment, all of that, and then we've also come up with a bunch of rolling means and medians and sums and all that type of thing as well. So this could really give an analyst the ability to dig into a lot of different angles of this. There's also that summary file that I talked about. And so, for example, this will be the yearly summary statistics for precipitation throughout the entire year, basically. So these are daily values that are then summed and aggregated. And it's not just precipitation that we have here. We could look at a bunch of different features here, but we can just look at, for example, the min temperature. So this is the summary stats for daily min temperature in the year 1889. There's 1890. Going to freeze this header row. We can also look at subgroups, for example, in this as well. So let's look at the season as well. So this would be the summary statistics for the min temp in the year 1889 in the fall, and then we have spring, summer, and winter as well. So we're really able to slice and dice this data in a lot of different ways and get lots of different angles of summary statistics. In my subsequent analysis, I only look at certain variables just for time purposes, but again, if somebody were interested in extending this, there would be lots of different ways that they could look at and analyze the data. All right, so that's the data cleaning. And then, of course, we can do some data exploration. So there are simple things like making time series plots, looking at distributions, perhaps some more novel things where we look at how is skew and kurtosis changing over time. We can look at how autocorrelation is changing over time, which is kind of interesting. And then there's a function that I write for rolling KS statistics. So looking at, if we take a bag of weather in a set of years, and then we take a bag of weather in a subsequent time period, are those two drawn from the same or different distributions, basically? And this is written in a way where this can be pretty configurable, and that'll be a little bit more evident whenever we look at the output. And then this is set up to where we can pass in, different variables that we want to look at. Do we want yearly analysis? What seasons do we want to look at? And really in this analysis, I look mostly at winter and summer weather, just because that's when the results can be the most extreme. But again, a more thorough analysis could look at all the seasons. All right, let's take a look at what some of this output actually looks like. So again, we just have some histogram distribution. These are good to just get us a feel for the data. And one of the things that we'll notice is that variation is expected. It's whether or not the variation is correlated with time or if this is changing over time that we really care about. And one of the interesting things, but also challenging things about the weather data, it's not like in 1900 the average temperature was so much different than what it is now. That's not to say that small changes in temperature aren't important. They definitely are. But, when you're dealing with, have average temperatures gone up by, 1 or 2 or 3 degrees or something like that systemically over time, just from a statistical perspective, that's a little bit more tricky, just given how a lot of these methods want preponderances of evidence. And so there's kind of this challenge of how do you sometimes detect kind of these small but systemic changes. And that's one thing that I'm still working through. So variation is expected. We also have some time series plots. So if we look at the mean of max temperatures in the summer, we can see that those have, kind of just hovered around probably some mean line here. So maybe not anything super systemic there. I think the min temperature one's a little bit more interesting. So this is the mean value of min daily temperatures in the winter. So we can see that, maybe there's more of a local effect here. If I were to just draw like a regression line through this, again, I'm just doing the eyeball test here, it'd probably be a flat line. But if we were to do regression splines, we could see that there might be a line here, a downward slope here, and maybe an upward slope here. But again, the idea of some of these plots is just to get a visual idea of what's going on in our data. What might be more interesting is looking at skew and kurtosis over time. So are the distributions of temperatures getting more skewed or having fatter tails over time? So, we can just look at the min temperature again. This looks like, when we're measuring skew over time, probably still white noise. There definitely are some local effects here. That's absolutely for sure. But again, that could just be some overarching pattern and not necessarily anything we need to necessarily be concerned about. And what I mean overarching pattern, just like the pattern, just like kind of the natural fluctuation in temperature is what I'm trying to communicate there. If we were to look at all of these charts, again, we might see some local trends, but it's hard to surmise that with this particular statistical test that there's much more than just white noise. But again, we're just kind of looking at specific facets of distribution. So let's just take a look at one of the kurtosis ones. So obviously there's a huge outlier here. I'm not sure what happened there, but that kind of obviates a lot of the other patterns. Yeah, so this is extreme highs. So this deals with, I think I set temperatures above like 95 degrees, and this looks at the rolling mean of that in the summer. So this would roughly correspond to periods of sustained high temperature. So we can see that, again, really hard to discern a pattern from the eyeball test here. So that was, I guess, one other thing before I go to the KS test. So I also looked at autocorrelation over time. So how correlated are yearly temperatures with past years? So in other words, if I knew, and this deals with summary statistics. So when I am looking at autocorrelation, I am throwing in the summary data as well. So this is for this year and season, or for this year, what was the mean temperature? What was the mean max temperature? What was the mean min temperature? I know I'm throwing a lot of words here, but really the idea is, if this is 2025, how predictive is 2024 of 2025? And how predictive is 2023 of 2025? And so on and so forth. And we can run this calculation in an expanding way so that we can see that has the autocorrelation changed over time, because we can measure autocorrelation in 1910, and then we can update that calculation in 1911 and update it again in 1912. So I thought these results were kind of interesting here. So let's look at just the mean temperature. So we have the different lags, and so we can see that really it's just noise to start out with, and this is to be expected. Like, you're going to need several observations before an autocorrelation becomes stable, basically. But we can see that there is kind of this bump here around, 1985 or so, where things change a little bit. And you could potentially make the case that these are trending towards zero, so that weather over time doesn't do a good job of predicting weather in the next year. Again, I know that's a word salad potentially, but we could say that potentially the autocorrelation of yearly weather values perhaps does not perhaps declines over time, because we can kind of see these things moving towards zero. If we look at another one, we can see sort of kind of the same pattern here. Again, things are going to be noisy for a while. This could just be a facet of the sample size getting bigger, and it may not necessarily mean that there's a statistical trend, just that things are becoming more stable as time goes on and the statistical calculation has more data to smooth itself out. But again, there might be this trend towards yearly autocorrelations trending towards zero, which would again mean that perhaps when just doing a pure statistical approach, that results are perhaps less predictable over time when looking at yearly summary values. So just something interesting. I don't think anything conclusive, but perhaps an interesting application of autocorrelation. So not just looking at it in one point in time, but looking at how autocorrelation, or how a value is correlated with itself, changes over time. So that's my cat, Leo, who apparently wants to be involved in this. I don't think he knows very much statistics. So one thing I wanted to talk about was the KS statistics. So this is where we can determine, are two distributions the same or different, more or less, or if we have distribution A, is it drawn from a different process than distribution B, would be another way to kind of couch that. And so when we looked at skew and kurtosis and means and distributions and all of that, number one, we were kind of using the eyeball test, but specifically with skew and kurtosis, we were just kind of in isolation looking at different facets of the distribution. So the KS statistic will look at the entire distribution. So let me look at kind of the CSV result of some of these. And now Leo is playing with a ping pong ball. So that is what you hear in the background. Again, we're going to keep this informal. This is just something that I want to share. I am not too concerned if this is overly polished. So what we have done here is we have said, okay, give me all weather data from 1889 to 1893. So give me a 5-year segment, and then determine, is the data in this next year drawn from the same or a different distribution, basically. So is 1894 data, weather data, and I think this is just using minimum temperatures and winters, is this drawn from a different distribution than the 5 years previous? And then we do this in a rolling fashion. So then we take 1890 through 1894, test against 1895. So this is looking at, is weather changing over time in respect to, are there breaks in the distribution in which weather occurs? And Leo is driving me nuts with his ping pong ball, so I'm going to go fix this real quick. Again, I'm just not even going to edit this. All right, we're back, and he is looking at me kind of disappointedly. He'll probably find other ways to make noise. Oh, yep, he has found a jingle ball and is doing that. So hopefully this is some comedy as well, along with statistics. All right, so back to where I was. So again, we are running these rolling KS statistics. And so we can see that in this particular case, that weather from 1894, specifically looking at the distribution of minimum temperatures in winter, this was drawn from a statistically significant distribution than the previous 5 years. We can see that's the same case for 1895. So what we could surmise is that kind of in this period, there's a lot of changing weather, basically. And so we can also just kind of look at what was the average min temperature, and we can see that it does kind of oscillate a little bit in this period. Again, just comparing trends year over year. And so the thinking is that if the rolling pattern of statistical significance goes up over time, then that could be an indication of more weather change or more weather variability over time. Not necessarily saying temperatures are going up and down, just that things are different over time. So again, this might be a little bit of a novel application of this, but again, if we see that things are consistently being drawn from different distributions more and more over time, that could tell us something. So I actually have some plots of this. Yeah, KS test. So if we look at just, this is the rolling statistical significance over time. So that's that last column that we looked at. And again, this kind of looks like white noise to me. There are local patterns, but not anything that's systemically changing over time. If we look at, for example, max temperature, yeah, there could be some local effects here. But again, this might be kind of an interesting or novel way to apply the KS statistic to help ascertain if there are changes in variability or reductions in predictive power over time using a very simple statistical test. So what I would encourage you to do is kind of take a look at this function here. It's written pretty generally, and so we can definitely adjust this as needed. But one of the things that I like about how this is set up is that we're doing 5 years against 1 year. We could do 5 years against 5 years, 3 years against 3 years, 5 years against 2 years. So this is set up in such a way where we can kind of vary this quite a bit, and then kind of do some interesting things with it, I think. All right, so that was kind of the general data exploration I did. I also did some classic k-means clustering, which you can never go wrong with. So in this case, we're doing the summary data, and we're trying to determine, do clusters change over time as well? Now Leo is playing with the computer cord. All right, so the thinking is that if we are able to find good clusters of data, then those should be fairly evenly distributed over time. And apologies if the audio cut out there. I had to take away the computer cord from Leo. Again, I hope this is entertaining for people, and I am not taking the time to edit. I just want to share what I'm working on, and hopefully this is entertaining for people as well. I'm not sure if anybody will even watch this. So we do just classic k-means clustering. We do a silhouette score here to determine the optimal number of clusters. But again, the thinking is that if there is not much variability in weather over time, then, if we find 2 clusters, then, for example, decades should be roughly evenly represented across clusters. So again, if we have 2 clusters, we should see, 5 observations in 1950s, 5 observations in 1960s, 5 observations in the 1970s. Again, there could be some statistical variation to that, but we can also use clustering to determine, has there been potential variability changes over time? So again, we do this with min temperatures in the winters and max temperatures in the summers. This is modeling, clustering, and so we can kind of look at these results here. So this is looking at the number of occurrences per decade, and I just chose the first cluster, so cluster 0. So we can see that this does change over time. It's not necessarily systemically going up because of this, but this is basically saying that, hey, in the 1940s, there were 6 of the years were in cluster 0. But then in many of the most recent decades, it was more so, 8 or so clusters, which we're in this cluster 0. So the proportion of years that appear in this cluster change over time throughout the decades. Again, I know that's a little bit of a mouthful, but again, maybe you can kind of see what I'm trying to get at here. If we look at the summer, we can see that, maybe this one has changed a little bit over time. So this is saying that, cluster zero, if we look at the first several decades, like almost all of the years were assigned to that first cluster. But now in like the 2010s, only half the years in these decades were assigned to this particular cluster. So it doesn't make as much difference what these clusters say. It's again that, if there were no changes in weather over time and the summary statistics of weather over time, that we would expect this to just be roughly a flat line with maybe some noise. But if more or fewer clusters are represented in different proportions over time, then that could be an indication of some weather change. Again, what we don't see here is like a strict upward or downward trend. This could just all be random noise or local patterns playing into the results. But again, there could be some applications of clustering to actually look at variability over time, which is kind of the heart of this is, how do we think about variability? How do we try to measure variability in some novel ways? Okay, anomaly detection. So I kind of just did a heuristic on this. So I chose my variable. I said, hey, kind of calculate a rolling value of this of 7 days. And then if there is a temperature value, in this case, a min temperature that is 10 degrees off this rolling value, then flag it as an anomaly. So not anything that's super novel by any means, but kind of a stab at some time series anomaly detection. And so that's definitely one thing that's very important with time series data is making sure that you're treating everything sequentially. So if we were to just throw this into an isolation forest, for example, it probably wouldn't produce the results that we want because that methodology is not time aware. So this looks at how many anomalies are different than expected over time. And I should actually probably go back and explain some of the code to that. So this is basically another expanding calculation that looks at for every week, how many anomalies should I expect in the temperature? And then this kind of looks at, is this different than expected, basically. So for every week, we can say, based on historical data in an expanding fashion, how many anomalies should I expect? Because temperatures are going to change over time. And then we can look at, okay, what is the difference in the number of weekly anomalies that we get from what we would expect based on historical data. And again, this might be a little bit more clear whenever you look at the code and look at the function and run the results yourself. Again, I'm just trying to give kind of an overview here. But again, this is, if this is at 0, basically this is communicating that based on historical precedent, we've experienced the same number of anomalies as we would expect. So obviously this is going to change over time. And again, if you heard that in the background, that was Leo who found another ping pong ball. But again, if this is at 0, then that means that we have expected the same number of anomalies that the historical data would indicate. If it's higher, then we're getting more anomalies. If it's lower, we're getting fewer anomalies. Again, this looks to just be probably have a mean of 0, so this would just be white noise. That kind of these local anomalies are perhaps not changing over time. It's possible that if we eyeball this, there might be something going on here. But again, my eye might just be biased by this thing here. And if I were to just look at this segment, I would probably be more likely to say that's white noise. So again, this is the reason that we also do statistical tests that we've talked about in the past, is that it kind of takes out the bias of just looking at the data. One really interesting application, and this might be my favorite thing in this project, is change point detection. So this is different from anomaly detection. Anomaly detection is generally a lot more sensitive. Change point detection by nature is time aware. So this is kind of one application that looks at a time series and tries to isolate when a systemic change has happened in that time series. And there are ways that you can kind of tune the thresholds a little bit here. In this particular script, I kind of just do a vanilla implementation, and most of this is just boilerplate to actually get this to run on my laptop. So again, I won't explain this, but there's kind of a chunking strategy here, because if I were to run this on the entire data, my laptop just can't handle this. So I kind of run chunks of years and do change point detection, and then overlap those chunks and then dedupe the chunks as well, to make sure that we're not over representing certain years. But if you want to, you can definitely look at the code for that. But this is also potentially a methodology, since we're sort of like bootstrapping this and then pasting the bootstraps together. This might be a way to reduce overfitting as well. But anyway, change point detection kind of helps us figure out where's there's been a systemic change in a time series over time. So in particular to weather, this would be changes of season, right? So when is a change of season detected? And we would expect this to roughly happen 4 times per year. That's back to clustering. What I want is change point. So this looks at, if we're just looking at min temperatures in this particular case, and Leo has somehow found another ping pong ball. He has had these stashed and he has waited to play with them while I am trying to do this video. Again, we're keeping it informal here. All right, change point detection. So each of these are a plot for when a change point has occurred. And so let's look at 2015, for example. I think something weird is going on with 2014, but for most of these years, I'm going to have to look at what happened with 2014, but there are, generally 4 points or 4 change points that have occurred in that year. So 2015 is a good example. So this would be kind of a change point in week 10 of the year. This is a change point in, say, like week 22 or 23, a change point in week 40, and a change point in, say, week 47 or 48. So it doesn't necessarily matter where these occur, but are the changes in season being detected at different points in time. So I would love to figure out a statistical test on this. Right now I just have a visualization, but this kind of says that, there's normally a change point, within the first 10 weeks, but that changes over time. So the first change point in temperature does kind of vary a little bit. The second change point looks to be a little bit more stable. Things get really kind of wonky when you're looking at a fall change point or a winter change point. Is like, this third change point here maybe does something like that, if you were able to follow my cursor there. So I think this is interesting. So this is kind of an unsupervised way to figure out when the seasons are changing based on temperature alone, a statistical trigger. And so this can kind of look at, is winter, has a change point that indicates winter, has that occurred earlier or later than what we would expect? And again, some natural variation is kind of the default here, but this is kind of interesting. So the last thing here is actually some machine learning modeling. So kind of looking at, does predictability of weather change over time when doing a machine learning approach? And if it does, that could mean that variability has increased, which degrades the performance of a machine learning model. So we build a bunch of different models here. We are just kind of looking at gradient boosting for the most part. So, the mean, we also do predicting the mean. We also do some quantile regression to kind of analyze that as well. We also do it through our ridge regression, and here I'll explain that a little bit more later. We do some custom time series cross-validation. So again, we need to cross-validate in a way that's time aware. We can't just throw a bunch of years randomly into cross-validation folds. This uses HyperOpt to optimize the parameter. So I'm not trying to build a great model here, but what I'm trying to do is determine, are there changes in model behavior over time, which again can kind of be difficult to detect whenever you're building a time series model in and of itself. But it's a approach to potentially trying to look at variability and does predictive power change over time. So I ran all of these models. That's in the folder ML. And so let's just look at the histogram gradient boosting. Let's just look at when it's predicting the mean, so not any of the quantiles. So this is just the cross-validation scores. I think I just did mean absolute error for this. So this is our best model here, and we can see how it performs on all of the folds and all of that, and the hyperparameters that were chosen for that best model. We can also produce all of the predictions here. So obviously there's going to be some bias here because the model was trained on this day here. So we try really hard in this model to fight overfitting, but again, the model was trained on this day of data, so there could be some level of overfitting. The way we did cross-validation is it wouldn't be trained on kind of this last segment. I would have to check how big I did the year chunks. So again, how time series cross-validation works is, you train on 2000 and then you test on 2001 in the first fold, and then in the second fold you train on 2000 and 2001, and then you test on 2022. So at the very end of that, there's going to be a fold that you don't train on. There's going to be just like a natural holdout there as well. So the last few years in this data set were actually never trained on, so they provide like a true holdout. But we can kind of look a little bit more at that later. I also run permutation importance. Some of the features that we engineer, since this is cyclical data, I guess I probably should have started with like, what are we even trying to predict? We are trying to predict I think we did max temperature 7 days ahead, given only data that we would have known at that point in time. So for example, today is April 14th. I would try to predict April 21st, the max temperature, and I would only be able to use data that I would have known as of today. I would be able to use no data from April 15th through April 21st. So that's how we kind of set up the simulation here. And obviously the time of year can be predictive in making, trying to predict temperature, basically. And so we can turn the day of the year into a cyclical feature by calculating by converting that into a day number and then calculating the sine and cosine. So this is a classic cyclical feature. So those are actually our top two features, would be the cosine and the sine. There are also some rolling temperatures. We actually don't use year with most of the models. So this is 0 because it actually gets dropped in the pipeline, but it still appears there because it gets fed in to the scikit-learn pipeline, but then gets dropped. I'll kind of talk about why we do that here momentarily. But this kind of gets us an idea of like what's important. The model's not very good, as you can see. So if we go back to the CV scores, this is just mean absolute error, so directly interpretable. So on average, the model is off by like 8 degrees for the most part. So obviously, like, there can be good predictions and bad predictions if we just look at kind of this raw data. So, this is a good prediction, predicted 38, the actual was 36. Here, the actual was 26. This was 37. So this kind of makes sense as a prediction. There was a big drop here. Didn't catch that. So this really shows kind of the flaw of using just straight statistical methods to predict weather, and why having supercomputer simulations is actually so valuable and important here. So the other thing we can do is look at what are the errors by group. So again, there will be some bias here, which is to be expected because some of this data the model was trained on, other parts of the data was just like a straight holdout. But we can still take those raw predictions on the entire data set, knowing this is imperfect, and look at what are errors by group. So in 1889 in the winter, the average error was 12 degrees. In the spring, it was 7 degrees. In the summer, it was 4. In the fall, it was 8.2. So there are kind of some interesting things where things seem to be more predictable generally in the summer, less so in the winter. That kind of holds again if you just kind of look at even the most recent things. And again, this would be a true holdout. The model was never trained on these last few years as well. And so what we want to look at is this changing over time? So are the errors, the prediction errors per season changing over time? Which again can be a little bit tricky because there might be some concerns with overfitting. And also the model might just get better over time because it has more data. So this prediction error may not be because the model, the data is easier to predict. It could just be that there's more data as well. But again, if I were to look at this, looks a lot like white noise to me. There could be some downward trend here with predicting the summer. But again, this could just be downward because there's fundamentally just more data to train on as we're doing this time series cross validation. I'll pick a random one for if we're doing quantile regression with the 25% error, or not 25% error, but trying to predict the 25th quantile. And my cat is meowing again and trying to distract me from finishing this out. Kind of the same story here. So again, not necessarily promising results, but potentially promising application that could be improved with some pivoting. So I did mention that in certain cases we throw out, or actually in most cases we throw out year, but with the ridge regression we kept in the year because I wanted to control for the year to see how much attribution the model would just say, I can't figure out what's going on in 2000. I'm just going to dummy that out, basically. And so we can look at the permutation importance will basically just report a single value for the year. We don't really care about that, but we can look at the coefficients. So these are the log odds from the ridge regression when we allow it to condition on year. And so again, the thinking is that if the model puts a lot of attribution into certain years, and if this is systemic, then certain periods of time may or may not be, or may be more difficult to predict because the model is basically just like throwing attribution at the year itself because things were kind of wonky in that year potentially. And so an example of that would be if we saw years 1900 through 1910 appear really, really high here, it could just be that the model was able to pick up on some effect for that year, for those years, and just, was able to model that period well, and then just assigned attribution to kind of these dummy variables to dummy them out, if you will. Again, this is just an idea. We're testing some hypotheses here. But we can see that there are a lot of coefficients for years that are pretty close to zero. There are some that are bigger on both the positive and negative side. But really, if I'm just kind of eyeballing this, I'm not seeing anything that's super systemic here. So I'm not seeing a bunch of 2010s or 1950s systemically here. It looks to be kind of randomly distributed. Again, I could test that probably a little bit more thoroughly. But again, just kind of the eyeball test of this. So again, repository is here. This has definitely been a fun project to work on. Would love personally to continue to work on it a little bit. And again, the whole goal of this was just to share a little bit about the project, the data, some of the results, kind of how I looked at this from a statistical perspective. Again, I wanted to try to employ some potentially useful statistical methodologies in a novel way to try to measure variability and changes in predictive power over time. So nothing conclusive, but really this was to kind of look at, how can we come up with some interesting ways to look at this weather data. So if you want to, feel free to pick up this repo and go from there. really enjoyed kind of working through this and sharing this with you. And I hope you enjoyed some of the unintentional comedy that happened along the way with some of the cats.